Hello, students. Checking in with 13.2, going over some areas now, areas of polygons and circles. Again, our Common Core standard here starts at grade 3. Students should be able to apply area and perimeter formulas for rectangles. By the time we get to grade 6, we're talking about right triangles, special quadrilaterals, and polygons. So between grades 3 and 6, we're continuing to use area in many different ways. Now, area can be found in quite a few ways. We have tended to define it in one way that seems to be easiest, which is this way. Area is measured using square units, and the region is the number of non-overlapping square units that covers it, and that's the area. So, for example, if we drew a shape that was 2 feet by 3 feet, we could break that shape up into non-overlapping squares, and we could kind of count how many squares that is, and this would be 6 squares, but each square is 1 foot by 1 foot by 1 foot, and 1 foot times 1 foot would actually give you 6 feet squared. Now, you could also write it this way as square feet. So either one of these is perfectly fine for me. And it just kind of depends on your preference. Each one is fine. But we got to be careful here. There's a big difference between 6 square feet and 6 feet that are being squared. That would be like a square that is 6 feet by 6 feet. That is not the same thing. You see, 6 feet times 6 feet would be 36 feet squared, or 36 square feet. Okay, so a little bit of caution there to be used with our notation. Okay, couple of ways to do areas, and this is the areas on a geoboard. Remember the geoboard with the little pegs. And so as you kind of map off a shape, the area that it would be on the geoboard, we can think of 1 square unit as being that little square right there. So as you go through and calculate, you could say, well, wait a minute, this little triangular piece, that's half of a square unit, right? So that's a half. The next one up here would be 2 square units, then another square unit down here, and then this last one, let me clear my other pieces off. But if you look at this triangle right here, you can see that it is half of this rectangle. The rectangle would be 2 units. This one's half of it, so it must be 1. So you get 1 plus 1 plus 2 plus a half. 1 plus 1 plus 2 plus a half. That's how you can find the area. So again, as you come down here, you can just break it up into small pieces. And that's what they're doing here. They're breaking it up into triangles, squares, rectangles that are very easy to compute. Right? Another method of finding the shapes is the rectangle method. And the rectangle method, we construct a rectangle around it, right? Then we find the shapes that we don't want and we remove them because we think that's going to be quicker than trying to go the other direction. And so anyway, that's another completely fine approach. So again, what we're trying to find though is we're trying to find this shaded, like we want this. That's what we're trying to find. But it doesn't make any really nice, like the triangles that we try to find aren't really nice and easy to compute. So instead we'd go, okay, forget that. Let's go too big, right? Let's go bigger than what we need, and we'll just take out the pieces that we can easily compute, and what's left would be the orange area, okay? And so this is an idea that I've referred to in other parts of the course as big minus small. We did this with the clock geometry. We're trying to find how the hands make a 90-degree angle or so forth. Okay. So there we go. If you're trying to find this shape or this shape next to it, you do have a couple of approaches. I think personally, the rectangle approach is often good when your triangles are harder to compute. Like this weird triangle that I'd have to try to figure out what's the area of that's weird. So instead, I would probably come along and do the rectangle approach and just say, hey, let's get too big. And what that means is right here, this is 1, 2, 3, and 1, 2, 3, 4. So I have 3 times 4, which is 12 shaded right now. And then just mark off what you can see. So like I can see this triangle right here, right? And that is half of a 2 by 3, which would be 3 units. So I'm going to remove 3 units for this one right there. Next to it, I see a small triangle. That's a half a unit. And next to it is another square, which is just 1 whole unit. And up here, there's a triangle that's a half a unit. Well, half a unit and a half a unit is another whole unit. That's fine. Up here, this is a 1 by 2, and up here is a 1 by 2. So that becomes taking away 2, and I have 1 more at the end. So that's the idea of kind of taking away all the pieces that I can actually see. And as I take a look at it, this one would be 12. I got a 3, I got a half, I got another half. So 3, 4, 5, 6, 7, 8. So I take away 8 from 12, and it leaves me with 4 square units. And that's kind of the way that you can use the rectangle approach. Again, it's just a little bit easier at times than trying to find what's the base of this triangle, what's the height of the triangle. Although, let me zoom in and show you that you could do it that way. And it really, like I said, does depend on you a little bit. Okay, so let's see here. If I was going to do, let's see here, this one. So I'd probably break those up right there. That's a half and a half. Okay, so that's 1. And then over here, I'd break this one. And this one right here is a 2 by 1, but I have half of it. So that's +1. Now the last little bit that I have is, let me erase this unit over here, is this kind of weird triangle. And that's where it's really going to be helpful if you do remember how we form triangles. Triangles are base times height. And so if you think of this triangle right here, the base could be this piece right here because it's 2 units, and I can count that very quickly. But then the height has to be that perpendicular component, which would be right here, which is also 2 units. So it's a base of 2 and a height of 2, but because it's a triangle, I only have half of it. So I would add on 2 units for that. And 1 plus 1 plus 2 gives me 4. So again, 4 units one way, 4 units another. It's up to you to decide which way you like better, but each of them is going to be the same. Let's see, you're converting units of area. So the same system that we used before, which is create your fractions, put what you don't want on the bottom, what you want on the top, and work your way down. Perfect. Everything there is fine. The English system, we tend to use square inches, the square foot, square yard, square mile. And in the metric system, again, very similar. So here we go. Let's do a little converting. And the reason that we have to do a little bit of converting is that the relationship does change. So when we're dealing with square units, if you can think of King Henry's dear mom drinks chocolate milk one more time. King Henry's dear mom drinks chocolate milk. When it's linear, that means we're dealing just with meters. Then we're going to move 1 per step, 1 decimal point per step. But when it's square meters or something along those lines, so we're talking about area, the square here tells you to move 2 per step. So this is kind of a nice piece right here. So watch this. If I'm going from centimeters to millimeters, normally I would go 1 step, but because it's squared, I count that as 2. Every step becomes 2. So I put my 5 down, I put my decimal point, and I move 2 spaces over, and that becomes 500 square millimeters. Okay, down in the bottom one, if I'm going 124 million square meters, again, I don't want to try to memorize this. I don't want to memorize this table. I hope you don't want to memorize this table because it's a pain. Find where you're starting. I'm starting in square meters. That's what it says. And I want to move to square kilometers. So I'm going to go 2, 4, 6 digits. That's what I'm going to do. Okay. So if I have 124, what is that, million? I'm going to move 6 decimal places. So on the number 124, 0, 0, 0, 0, 0, 0, my decimal point is right here. And all I do is move 6. So it's 1, 2, 3, 4, 5, 6. I end here, and I'm at 124 square kilometers. Again, I don't want to memorize the table. I honestly don't want to do it the way they're showing here. I'd rather use 1 step, 2 steps, and when we get to volume, if we do use volume as cubic centimeters or cubic meters, it will just be 3 per step. So straight lines are 1, area is 2 because it's 2-dimensional. Am I doing volume? That's 3-dimensional, so it would be 3 per step. Meant to be very quick. Gotta love the metric system. Now, we do run into issues in the non-metric system because what you memorized before doesn't seem to work. And I got to tell you, I do not want you to memorize this. Right? Some of you are going to try to do it anyway. Oh, help yourself. But I'm telling you, there is an easier way. If you think of a box that is 1 yard by 1 yard, the box would be 1 square yard. But if I turn that exact same box into feet, I get 3 feet by 3 feet, which would be 9 square feet. So again, you might be thinking, oh, it's not the same. It used to be 3 to 1. Now it's 9 to 1. Here's a fun fact. It's always 3 to 1. We're just squaring it. So when you write it out, and we'll do a conversion factor here just to kind of demonstrate that. Let me get some white space. When you write it out, do the same fractions you did before. And then I'll show you 2 ways that you can go about it, and I'll let you take your pick as to which one feels more natural for you. Let's say that we had 7 square yards. At the end of the day, I want to turn this into, let's see, I'll just say square inches. Okay. I don't have it memorized. I don't want to memorize it. I want to get rid of square yards. What I want you to do is I want you to think of this as 7 times yard times yard, because that's what yard squared means. So when you multiply and you say, I want to get rid of yards, 1 yard is 3 feet. I need you to see, and that's why I want you to write it out this way, that one of the yards goes away, but you still have another one remaining. So option 1 is to just write out 3 feet per yard and 3 feet per yard. Now I need to get into inches. So I know that 1 foot is 12 inches. That gets rid of one of them, but I still have the other one with feet. So I need to do it again. 12 inches to 1 foot. Feet, feet. I'm left with inches times inches, which is inches squared. I grab my calculator and I just multiply. 7 times 3. Let me grab my calculator. 7 times 3 times 3 times 12 times 12. And there it is. So 7 square yards is equal to 9,072 square inches. Now, I said I'd show you 2 ways, right? This is one way. There's nothing wrong with this way. If you feel more comfortable doing this in this one piece right here, you can do this in 1 step. So let me show you what that looks like. If we start with 7 square yards over 1, then we would multiply by 1 yard and 3 feet. Now that looks identical. But here's where the fun comes in. You come up to the top and you say, I want to square it because I want to do 2 in 1. Now the yard squareds are going to go away with yard squared. You have feet squared, and you'd be left here with 1 foot to 12 inches. And I would square that because I want to get rid of square feet. So square feet, square yards, and I'm left with square inches. And this one could be a little quicker because now in my calculator, again, if you're using that scientific calculator, if not, use your phone sideways and just type in 7 times 3 squared times 12 squared, and you get the same answer of 9,072. So it's up to you which way you prefer, but please don't, wow, stop sharing. Please don't try to memorize this table. Okay, it's an exercise in futility, and it's going to get worse as we go on because 3 dimensions is going to be even bigger. So let's not do that. Okay, let's just keep this rolling with where it is. So as we measure land in the United States, gotta see here's some fun facts. If this was a question on a test, I would give you this information. There are 4,840 square yards in 1 acre, or we could use square miles, but square miles are huge compared to that. So 1 square mile is 640 acres, which is great. Now, historically, that came from the amount of land that a man with 1 horse could plow in 1 day. And I don't know how in the world they came up with a uniform measure because horses are different, men are different. So the amount you can plow in 1 day. And when is the day? Is it in fall? Is it in summer? I mean, so anyway, there's who knows? Who knows how they measured things back then? At least we're a little bit more standard now. So in the metric system, we have air, which looks like R, but is pronounced air. And then we have the larger one, which is hectare. And so a hectare is, again, a measure of larger pieces of land. And for very large measures of land, they use a square kilometer. So again, even though it's the metric system, they don't exactly do it quite the same way, but it is tied into some really nice numbers. So notice 1 air is 100. Okay, 100 airs is a hectare, which makes sense because that's what hect stands for, is 100 of these. Okay. And then a square kilometer is just 100 hectares. So you get this idea that it's 100 of this, 100 of that, 100 of that. Their system is really convenient. Let's move on. Waiting, because if you did this in elementary school, I could see, if you love it so much, why don't you marry it? Okay, well, maybe I will. All right. Let's talk briefly about now coming up with formulas for areas. So the area of a rectangle is a pretty consistent one, and it's one you probably already know. The area is length times width because we're just making a rectangular grid and counting all of the little square pieces. And this ties back into when we did multiplication back in chapters 3 through 5. Okay, so find the area of the rectangles, you simply multiply. If the units are not the same, make them the same. There technically is nothing wrong with saying, multiplying these together and saying 4 centimeters times 0.2 meters is equal to 0.8 centimeter meters. There's nothing wrong with that. However, the rest of the world would cry because it's not a square unit and we prefer square units. So either convert 0.2 meters into 20 centimeters, multiply those and get 80 square centimeters, or turn the centimeters into 0.04 meters, multiply by 0.2 meters, and you will get 1, 2, 3, 8. There we go. It's 0.2 meters. Sorry, just 0.2 meters. 0.08 meters squared. It doesn't matter to me. It's whichever you prefer. But remember, King Henry's dear mom drinks chocolate milk. And if we had 80 square centimeters starting here, and I went back over 2 steps, remember though, because it's area, each step is really 2. So count it off. 2, 4, move over 4 places. 1, 2, 3, 4, and you'd have 0.0080 meters squared, which is exactly the same thing we got. So pick one that works for you. I'm going to say that our default will be to keep the units the same, but do understand that I know that they don't have to be the same. Okay. Now, let's get into some other funky shapes because we can actually create areas of other shapes by doing some quick conversions, like dropping a perpendicular straight down. We know how to do that with our compass and straight edge. And so we have a right angle. Then take the cut piece and glue it on the other side. And guess what you have? Now you have a rectangle. So when you have a shape that's a parallelogram, it's still base times height. Now that works for an area of a rectangle or a parallelogram. Just be careful. In a rectangle, the base and the height are actual sides. In a parallelogram, the base might be a side, but the height is typically not one of the side lengths. If you just multiply the side lengths, it will not get you the same result. Okay. Now, if you want to see why, go back in GeoGebra and build a parallelogram and then adjust this point, drag this point where the length is fixed. And you'll be able to see, wait a minute, the area is changing as I change that piece. So that's why we use height and not side length. The side length would get us multiple different values of area. Very cool. Well, let's see here. You know what else is great? Is that if you had a rectangle and you just cut it straight like this, you really have two triangles then, right? So if you had a right triangle, you could build a mirror image of it right up here and use the rectangle formula, which is area equals base times height, to get that, but then realize I don't really need this one. So the area of a right triangle would be 1/2 of the base times the height, right? That makes sense. That's kind of cool. But what if your triangle wasn't a right triangle, right? It's just, you're like, oh, dang it, it's not a right triangle. You're absolutely right. Haha, right. That was a pun. So instead, make a copy of this triangle. And again, it's going to be congruent triangles. So this angle is the same as that angle, which means the lines are parallel. And because we copied it, this angle here would be the same as this angle up there, which again makes these other two sides parallel. And this weird triangle, if I clone it and make two of them, creates a parallelogram. And I know how to do a parallelogram. It's base times height. But again, I have two pieces and I only need one. So the area of a triangle, whether it's a right triangle or not, does turn out to be 1/2 base times height. And we get the exact same concept. So very cool. So again, if you don't have a shape that's perpendicular, that is a right triangle, you can always drop something down to create the right triangle aspect and you'll be good to go. You'll be good to go with a parallelogram. And once you have a parallelogram, it's just 1/2 base times height. And notice here, they do talk about how there are 3 different bases you could use and 3 different heights. And don't worry, all of them will get you to the same result. So when you pick a base of a triangle, you have to, so if you pick this long side right here to be your base, the height has to be perpendicular to that base. So the height would be here. In this case, the height would be inside the triangle. Oops. Now, if you had come over and you chosen a different base, let's say you chose this side here as your base, then I would need to extend that side to find the height, because remember, the height has to be perpendicular to that side. So this would be the height right here. So that's why you'll see B times H1, then A times H2, and C times H3, but all of them divided by 2. So there we go. Now, you could also use a really cool approach. If you wanted to. So this is a really cool, now try this. This is something you could do with kids. Make a triangle, no matter what triangle it is. Fold, find the midpoints of the sides, fold point B down till it touches right on, and then fold the other two sides, creating what looks like a beautiful rectangle. Of course, the height of the rectangle is 1/2 of the height of the triangle, and the base has been cut in half as well. And now you can figure out what is the area of this rectangle and realize that in order to find the area of the triangle, you need to have 2 of these rectangles because, again, it's folded up on top of itself. Use that. See if you can't use that formula to come up with the area of a triangle. Don't worry, you will get the same thing. Super cool. All right. Let's see here now. Oh, yeah. This type of question came up a little bit before in chapter 12. If I have 2 parallel lines the distance between them is exactly the same. And so if you had a length of AB, which was just on one of the lines, and you picked any one of the points up here and you made a triangle out of that, because the distance between the lines is identical, the area of this triangle will never change. And this is kind of a cool one to do with kids if you had GeoGebra available. Let's take a look and kind of show you what I mean. I'm going to jump over to GeoGebra. We'll go to Geometry Calculator, and here we go. So first off, I'm going to build a line, A, B, and then I'll build a parallel line floating. Oops. Let me click parallel line up here somewhere. And then I'll just pick some additional points. Actually, I'll just pick 1 point on that line that'll change, point D. Okay. And the reason why I pick point D is I can actually move it up and down the line, but if I go up and down, it won't change. If you grab C, it's going to move the whole thing up and down. So I'm actually going to hide C so I can't see it anymore. There we go. And now let's create a polygon. We'll create the polygon A, B, D. Okay, and then I'll come down to measure, and I'll say measure the area of that one for me. So I want you to take a look what happens as I move point D. What happens to the area? There, it's a right triangle. Right? Let me zoom back. So the base, you see the base from A to B, it's not changing. And the height, which would be the distance from D down, is also not changing. So you could drag this all over the place. And it's still 18.7. You could drag it to the point. Let me get rid of this thing. All right, just shorten that up. Can I do even more? You could do even more. If you look at this now, it looks like you're like, there's nothing in there. It's the same amount of area as what I had over here. It's exactly the same. So no matter where I move this to, it's 18.7 the whole time. All right, fence problem. I'll let you take a look at that if you're interested. And then we've got find the areas. So if you got a parallelogram, base times height. If you have triangles, base times height divided by 2. If you have a kite, I know it seems complicated because you're like, wow, it's such a weird shape. It looks like a weird shape, but once you cut it, remember the diagonals are perpendicular. So take one of the pieces and just shift it up to the top. Take the other triangle and shift it up to the top. And because we had right angles created with that, we will end up with a nice, beautiful rectangle. Right? That's all we're going to have. It's just going to be a rectangle. The rectangle, though, the height overall of the rectangle is half of the original height of this shape because, again, we put it and kind of stacked it together. But the length of this shape, D1, would not change. So I have half of D1 times D2. Honestly, to me, it would be D1 times D2 over 2. But when you simplify it, remember, multiplication is commutative. So you really could just think of it as 1/2 times D1 times D2. Okay, so if we had a trapezoid, so many different ways to do a trapezoid, right? Yeah, I'm not sure how the best way is to do a trapezoid. Oh, wait, I've seen 3 different techniques. Let's pick one of those. So if I had a trapezoid and I was trying to get the area, then I know I have this thing, which would have, because they're parallel, I'd have to have a height. I have to have like a base 1 and a base 2 because they're parallel. And then, okay, here's what I'll do. I'll do a couple different techniques. Let's see if it helps. I'm going to take a complete carbon copy of this, and I'm going to put it right next to it like this. See it? So this becomes base 2. This is a base 1. The height stays the same because they're parallel. And now, but look at the shape. This is a parallelogram, right? It's a parallelogram. It's a parallel, and the opposite sides are congruent. This is a parallelogram. So to find the area of a parallelogram, we knew it was base times height. The height is h. The base is this entire piece, which is just b1 plus b2 times h. And there it is. That's it. That's one way to go about doing this. That's how you can find the area of a trapezoid. Okay, so and you don't even need that formula if you say just, hey, let me just build another one of them right here. Okay, got it. Base times height. All right. Okay, so let's take a look. Let's try it a different way. Okay, what's another way to do it? Okay, so I'm going to build a trapezoid again. Trapezoid looks something like this, right? Okay, now watch this. Here's what I'm going to do. So here's B1, and the big piece down here is B2. And this time I'm going to cut perpendiculars straight down. So this is B1. Okay, so I can find the area of this really quickly because that's just a rectangle, and the area of that is base 1 times the height. That's just that piece. Okay, so what's left behind, now what I can do is I can cut out the middle piece because I'm done with it and just smash the rest of it together. And what I end up with is a triangle then. And the height of the triangle is exactly the same as the height from before because that didn't change. That's h. And the base of the triangle would be whatever's left. It's b2 minus b1 because I had a long one, but I cut out some piece in the middle. And so the area of this is a triangle. So it's 1/2 times the base times the height. And so to find that trapezoid, you just add these two together. And it looks a little complicated, but let's take a look. So I'd have B1H plus 1/2 of B2 minus 1/2 of B1 times H. And so that's B1H plus 1/2 of B2H minus 1/2 of B1H. And thankfully, these are like terms. But one of them does have a fraction, so I will make this one have a common denominator fraction. And so I have 2/2 in the front. I have 1/2, and I'm subtracting. So my final result would be that I have 1/2 B1H plus 1/2 B2H. And that'd be it. If you want to factor out the common terms, you can. It's a 1/2 H that we factor out, and we have a B1 plus B2. It's exactly the same formula we saw right before this. So same formula. You could choose to do many other techniques. I've seen a lot of other techniques, and there's some cool ones out there. But it's completely up to you at some stage. If you want to do a trapezoid and you say, okay, how about this, Scott? Why don't I cut this in half? Like go straight down here, right? And then cut this like in half, fold this down, then it makes a little like a rectangle. Fold this one down, that makes a little rectangle. So this becomes here, this one comes down here, and then I can do it that way. And I'm like, go for it. Go for it. Nothing wrong with that. Absolutely. Okay. And then you can even say, well, let me cut this off and bring this down on the side. So it now just becomes one great big rectangle. Absolutely. 100%. Go for it. But at the end of the day, what you're going to see is what you end up looking at is that the bottom, you have half of the height, right? And then you have the base 1 times base 2 doubled. And so that becomes the issue at the end. So that's why you get the same exact formula. So there's trapezoid. There we go. And which one did they do? Okay, yeah, they did some other stuff by dissecting with heights and midpoints. I mean, yeah, sure, that makes a lot of sense. In any case, I kind of like the way I showed it. The way in the book isn't necessarily bad, but it is different, so please check it out. All right, last up for polygons, the area of a regular polygon. Now, the area of a regular polygon, you almost want to think of it kind of like a circle, because that's as they get bigger and bigger, they start to look more and more like a circle. So we don't call it a height anymore, but it is like a height of a triangle that is formed with the outside and then going up into the middle with the to the center of the shape. So that height, we actually, there's a word for it, and it's not height because it's not actually a height of this thing. We call it the apothem. And so what you'll do is you'll say, hey, I have the apothem, which is A, times the side length, which is S, and I divide by 2 because it looks like that piece right there is a triangle. And then you just count how many of those pieces you have, and you will have the total length. So notice I have 1/2 times A times S, but I happen to have 6 of them, so my end result is 3AS. Okay, there you go. But that was great because it was a hexagon, right? What would it be if it was a heptagon? So if it was 7-sided, well, I'd still have triangles on the inside of AS, and it would look exactly like this. Just out here, I would say times 7, times the number of sides. So what I end up with is the number of sides times 1/2 times A times S. Okay. And if you want to simplify, they do provide a little way of trying to simplify this a little bit if you happen to think about this shape having a perimeter. The perimeter of this shape would be the number of sides you have multiplied by S, because again, it's regular, so all the sides are the same. So this is the perimeter. And maybe we'll call that P. So then if you see n times s, that becomes the perimeter. And in this formula, n times s is here. So again, you could say that the area of a regular polygon is 1/2 times a, that's these, and then the n and the s come together to make the perimeter. So 1/2 AP is a perfectly legitimate way, or just say, wait, let me form the triangle and I'll just multiply by how many there are. It gives you the same result. So don't think you have to memorize that one. All right. Now, the idea here is they want to connect the idea of the apothem to the circle. Now, in a circle, the apothem is very, 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 very close to the idea of the radius. And so, if you think of all of those circles or all these triangles, you start getting closer to an infinite number of triangles. They're just infinitely small too. They're very tiny. And so as you get really close, what you end up with is 1/2 the area times the perimeter. So 1/2 area times perimeter. Well, the perimeter is the circumference in a circle. So that's pi times r. And it's really 2 pi r. Okay. And the A, which is the distance from the center out to the edge of the triangle, well, as the triangle gets more and more, that is really, really close to r. So you get 1/2 times r times 2 pi times r, and the 2's go away and the r's come together, and you get pi r squared. Now, there is the book page from the school textbook. I like that approach better when I'm working with younger kids because they can see that a little bit better. Okay, so let's take a look here, and we'll see it on page 829. But again, if you have that idea, the idea that the area of a circle is pi r squared, we can use that to find the area of a sector. Remember, a sector is a fraction of the circle. So take your angle, whatever it is, out of 360 degrees and multiply by the whole area, which is pi r squared. This is almost the exact same thing that we had when we did arc length, because arc length was just an angle out of 360 times the circumference. So that's the only real difference there between those. Very cool. let's take a look at the textbook pages, at least for the kids in elementary school. So if you take a look at this one, what they can do is they cut it in half, and they do color this one, so you can use color crayons to color this. And then they cut it, and they cut it into pieces. And what they end up with is this really, really cool pattern that looks very much like a parallelogram. Well, a parallelogram is base times height. So your height is a radius. Your base length up here is half of the circumference, because that's this piece right here that we have. It's half of the circumference. So the area of a circle is half of the circumference multiplied by radius. Now notice the circumference, of course, is 2 pi r. And so this, once again, is kind of a cool way to show, hey, the 2's go away. R times R becomes R squared. So the area of a circle is pi times R squared. All right. Again, this one was up in grade 7 when they were developing this one, but I believe this can actually be done with younger levels as well, but you do have to have the idea of what is the area of a parallelogram. Other shapes, break it up. Honestly, break it up, decompose them into familiar shapes. If you see something where somebody says, okay, ha, I'm going to put a rectangle and I'll put a half circle on top of it. They're like, aha, what's the formula for that? You could just stop and say, wait, I know how to find the area of a rectangle, and I know how to find the area of a circle, so I'll just do half of the circle. Okay, yeah, I can do that. Just decompose it. Don't make it harder than it is. Don't say, hey, what's the formula? We don't need a formula for this. And lastly, when we compare areas of similar figures. So if you have a similar figure, then how are the areas going to compare? So let's see here. So if I had a triangle right over here, and I'm not the biggest fan of their notation, but I'll use it because it's in the book and I don't want to. So the area of shape 1 would be 1/2 times the base times the height. So they're using little tick marks for ones, okay? Now, what I want to do is, let's say I want to double everything, okay? So that means the height over here is going to be 2 h1s, and the base over here is going to be 2 times the base. Then the area of your new figure, which would be half of the base times the height. Now that you know the base is 2 times, you'd say, oh, well, the base is 2 times b1, and the height is 2 times h1. Then we get 1/2 times 4 times b1 times h1. And the reason why I'm putting it this way is I know I could simplify the half and the 4, but I want you to look. I'm going to rewrite it as 4 in front times 1/2 b1 times h1. And I want you to see it this way. Because the area before was this, I have that exact thing right here, and I also have this thing that multiplies by 4. So when you double the scale factor is doubled, then the area will be 4 times as much. Okay? And that's because it was 2 times 2. If you triple it, if this is 3 times 3, it's not 4 anymore, now it's 9. So that's why when you look in the book, and it seems like it might be a little confusing, but if you take a look, if your scale factor is k, then the ratio of the areas is going to be k squared. That's true for any similar polygons. Okay, so if you know the area of one and you know the scale factor, you know the area of the other. All right. There's another textbook page from Student Books, and that wraps it up for 13.2. So hopefully that helps get you through it. If you have other questions, please let me know. I can meet you on campus on Zoom or in person, anywhere you need. I can also record a second video for you if you need it. Let me know. I'm here to support you. All right, off you go.